Friends, today we'll start with the question paper problem on trusses. This is the question paper from VTU finite element method, December 2014 and January 2015. Here we'll solve the problem on trusses. Here you can see the sixth B question for 12 marks. So find the nodal displacement, stress and reaction of truss element as shown in the figure. Take Young's modulus is 70 gigapascal and cross sectional area is 200 mm square. Here if you see here this is the truss element having two elements, first and second. It has two elements and application of node is over here. So we'll see how to calculate the stresses and displacement for this type of problems. So the same questions which you have written here. Now here the length of the first element, is 500, and the length of second element, this length we need to calculate. We can calculate by using Pythagoras theorem, that is 300 square, that is like root of 300 square plus 400 square, which you this answer means this is 300, then this is 400. If you use Pythagoras theorem, you can easily calculate the length of the second element, which is nothing but 500. Now these are the given data. In the given data it has given like the Young's modulus is 70 gigapascal, which we can write 70 into 10 raised to 3 Newton per mm square. Cross sectional area of the both the elements is 200 mm square. And as we know that the first step is to modeling and discretization for truss element. Here what we have done, like this is the first element and we have second element, and first element is connected between node 1 and 2. We have defined this node and we have defined this displacement. At node 1 we have displacement u1, at node 1 we have vertical displacement u2. Similarly here at the node 2 we have displacement u3 and u4. So each node has 2 degree of freedom. So similarly here the second element which is connected between node 2 and 3, and this node has displacement u3 and u4, which is already described here. Node 3 has displacement u5 and u6 because in the truss problem each bar element is considered as a two force member where each node has 2 degree of freedom, means it moves along x direction and along y direction. And as we know that in the given problem the application of load is at exactly at a node 2 in the y direction, negative y direction. It is in negative y direction, downward direction. So we'll proceed further. The second step is to determine the nodal connectivity table. Here what we do, since we have three nodes, node 1, node 2, node 3, we need to take a reference. From that we can define the coordinates of each node. Let us consider this as our reference. From this reference the node 1 is at a distance of 300 mm. It is already given in the problem. It is at a distance of 300 mm in the y-axis, and it is 0 at the x-axis. It is 0 at the x-axis. That's what we have written. In the x-axis node 1 is 0 and y-axis it is 300 mm. Similarly, if you see the node 2 which is at a distance of we can see here it is a 500, which is at a distance of 500 from the fixed point, and it is at a distance of 300 from the fixed point in the y direction. So if you see, that's what we have written. In the x-axis it is 500, in the y-axis it is 300. Similarly the node 3 which is here, it is at a distance of you can see the total distance is 500 plus 400, which is nothing but 900 in the x direction. Means the node 3 is at a distance of 900 from the fixed point in the x direction. Similarly, it is at a point 0 from the y-axis, means it has not moved any in vertical movement. It has don't have any vertical movement, in the sense it is in 0 position in the y direction. So that's what we have written the coordinates over here, 900, 0. So once you define the coordinates of each node, next we need to define the direction cosines. Here the direction cosines L and M for the first element is nothing but x2 minus x1 divided by L1, where x2 is nothing but this coordinate of second node, x1 is nothing but coordinates of x1, coordination of node 1 in x direction. So x2 minus x1 is nothing but 500 minus 0 divided by length of element, which is nothing but 500. 500 minus 0 divided by 500 will get 1. Similarly, y2 minus y1 is nothing but, here you can see this is y2, y1, 300 minus 300 will get 0. So we got the answers here. Similarly, we need to calculate the direction cosines for the second element. This we have already calculated, length of second element, that is nothing but we have applied Pythagoras theorem over there. Then we got this 500 mm square, 500 mm, this one. For this, as we know that this is the length of 300, this is the 400, then we got this answer as 500 by applying the Pythagoras theorem. Next, here we need to define the direction cosines for the second element. The direction cosines again given by L. L is nothing but direction cosines, which is given by x3 minus x2 divided by L2. Here if you see again nodal connectivity table, here x3 is 900, x2 is 500, x2 minus x3 minus x2 means 900 minus 500 divided by length of the element, which is 500, which we have determined. This is length of element. 900 minus 500 divided by 500 will get 0.8. Similarly, m, which we can define y3 minus y2, y3 is 0 minus 300 divided by 500. We got this answer, that is nothing but minus 0.6. Once we define the direction cosines, next we need to form a elemental connectivity table, where the first element is connected between node 1 and 2. The length of the element is 500 and direction cosines L is 1, M is 0. That's what we have found out over here. The first element direction cosines L is 1, M is 0. Similarly, for the second element, the direction cosines is 0.8 and minus 0.6, which we have found out here. Once you determine the direction cosines, next we need to move towards the determination of stiffness matrix for each element. Since we have two elements, we need to determine stiffness matrix for two elements. Stiffness matrix for truss element, as already discussed, it is given by A into E divided by L, L square Lm minus L square Lm. This entire stiffness matrix you need to remember, otherwise you can do one thing. Stiffness matrix is the symmetric matrix, so it is better to remember only the upper diagonal elements. So this is easy to remember. See here, L square M square L square M square, L square M square L square M square. Once you remember this, next step is to remember Lm minus Lm Lm. Next we have L square minus M square minus Lm. If you remember upper diagonal elements, then the lower diagonal elements are the same. See, since the first element, that is K1, is the stiffness matrix for the first element. The first element, if you see our first element is, this is our first element. Suppose it is our first element connected between two nodes, and as we know that each node has two displacement, u1 and u2, and here we have u3 and u4. So this element is connected between 4 displacements, so we can write here 1 2 3 4, 1 2 3 4, because single element, two nodes, each node has 2 displacement, we have 4 displacements, so we can write like this. So these direction cosines L and M for first element is determined over here, 1 and 0. If you substitute all this L, Lm minus L, you will get this answer, because before that we need to simplify this. Area is given 200, Young's modulus is 17 to 10 raised to 3, and length of the element is 500. If you simplify this, you will get this answer 2.8 into 10 raised to 4, where we have taken 10 raised to 4 as a common, and we have multiplied this 2.8 in this matrix. These are the elements, these are nothing but direction cosines. If you multiply with these elements, you will get this answer. 10 raised to 4 minus 2.8 minus 2.8 minus 2.8. These elements will get. Once we determine the stiffness matrix for the first element, same thing we need to determine for the second element, where we know the area is same, that is 200, and Young's modulus is 17 to 10 raised to 3, and length of second element which is given by 500. By using Pythagoras theorem, we have found out this length. Next, again the same stiffness matrix. Stiffness matrix for the truss element is, here it is 1 2 3 5 3 4 5 6. Why it is 3 4 5 6 3 4 5 6? See, here the second element, this is our second element which is connected between node 2 and 3, right? This node has two displacement in along x and y direction. This node has displacement along x and y direction. This is nothing but our u3 and u4. Here it is u5 and u6. Similarly, we need to write here 3 4 5 6 3 4 5 6. These are the elements which see here. Again, direction cosines L, Lm, which we have found out over here. For the second element, it is 0.8 and 0 minus 0.6. So those elements we need to substitute over here, like L square is nothing but L is nothing but 0.8, L square is nothing but 0.8 into 0.8, which is nothing but 0.64. Similarly, L into M, 0.8 into 0.6, which is nothing but 0.48. If you substitute all the element, you will get this matrix, and if you simplify this, you will get 2.8 into 10 raised to 4, and we have taken 10 raised to 4 as a common, and we multiplied this 2.8 we have multiplied with each element, and we got this answer. This entire the stiffness matrix. This is the stiffness matrix for the second element. Once we do that, next step is to form the global stiffness matrix, as we have already discussed how to form the global stiffness matrix in the previous videos. You can watch over there. Otherwise, see here, here, since we have truss element like this, right? Here we have node 1, node 2 and node 3. We have 3 nodes, and each node has 2 displacement, means we are getting 6 by 6 matrix, because each node has 2 displacement. 3 nodes means we will get 6 displacement, so global stiffness matrix should be of 6 by 6 matrix. So we have written here 6 and here 6 by 6 matrix. First, to form the global stiffness matrix, what we need to do, like we have seen in the first and second matrix. If you see, this is our first matrix where we have taken 10 raised to 4 as a common. Similarly, in the K2 matrix, we have taken 10 raised to 4 as a common. So in the global stiffness matrix, 10 raised to 4 as a common. Once we do that, the next step is you need to write these 1 2 3 4 5 6 and 1 2 3 4 5 6 over here, horizontal and vertical, that is row and column. Once we define that, next we need to define the elements, all these elements. To define that, first what we need to do, we need to see here, this is our first row and first column. This is our first row and this is our first column. Here we have 2.8. How this 2.8 came over here, we will see. If you see our matrix, K1 matrix here, this is our first row and this is our first column. We have 2.8. This 2.8 we have written over here in global stiffness matrix. Next, to determine this one, the second element 0, we need to see here, like this is nothing but first row, second column, we have 0. First row, second column. Again we need to go for first matrix. This is our first row, and second column we have 0 over here. This 0 we have written. Similarly, we need to calculate for all the rows and all the columns. Then you will get this answer, this entire global stiffness matrix. Once you got this global stiffness matrix, next what we need to do, we need to apply the boundary condition. Since in the earlier classes we have seen two types of boundary condition, that is nothing but elimination approach and penalty approach. Penalty approach is somewhat complicated, means it requires while solving the any problem with using penalty approach method, it consumes much more time, means we need to solve 3 to 4 equations. It takes a lot of time. So what we have done, like in the any problem on the truss, whichever problem asked in the truss, we used to go for the what we call elimination approach method. In elimination approach method, we simply eliminate the rows and columns. Here if you see our earlier figure, here this node 1, node 2, node 3, right? Node 1 it is entirely fixed and node 3 is entirely fixed. So in node 1 we have displacement u1, u2, and node 3 we have displacement u5 and u6. So we need to eliminate u1, u2, u5, u6. We need to eliminate u1, u2, u5, u6. That's what we have done here. So before eliminating that, we need to write this equilibrium equation, that is nothing but k into q, which is equal to f. Once we write this equilibrium equation, we need to substitute the global stiffness matrix, global displacement vector, global force vector. Once we substitute all these things, next step is to elimination approach. Here, as we know that first and third node are fixed, and the first node has 2 degree of freedom, then third node has 2 degree of freedom. So what we have done, we have eliminated corresponding rows and columns over here. So this is our first row and first column, and this is our second row and second column. Similarly, we have fifth row and fifth column. Fifth row, fifth column, this is the fifth row, fifth column, sixth row, sixth column. And if you eliminate all this, we get only these matrix, these elements, and these two and these two, because other elements are eliminated because we used elimination approach method. Elimination approach method tells that wherever the node is fixed, the corresponding rows and columns of the global stiffness matrix we need to eliminate. So once we do that, we get this. These are the elements which after elimination method, these are the matrix we got, like 10 raised to 4, 4.59 minus 1.34 minus 1.34, 1.008. So u3, u4, which is equal to 0. This is minus 12 into 10 raised to 3. Why it is here? See here. If you see this 1, 2, 3, 3 nodes, first element, second element, application of load is over here at the node in the negative y direction. So here f1 is 0 because it is fixed, and f2 is 0 since it is fixed, and f3 is nothing but this one here. This is f3 and this is f4 at node 2. This is node 2. This is our node 2, and this is our f3 and this is our f4. F3 and this is our f4. In x direction we don't have any force, so f3 is 0, and f4 is nothing but it is force is acting in the downwards direction, so minus 12 into 10 raised to 3, which you can see here, like in the problem it has given, it is acting in the negative y direction, which is 12 into 10 raised to 3 Newton, which is acting in the negative y direction. So we have written over here negative 12 into 10 raised to minus 3. This is nothing but our F3 and this is nothing but our F4. Once you write all these things, the next thing is we need to multiply row and column. What we have done here, first we have multiplied 4.959 into 10 raised to 4 into u3, which is equal to 0. That's what we have written here. Sorry, first what we need to do, 4.59 into 10 raised to 4 into u3. Next, minus 1.34 into 10 raised to 4 into u4, which is equal to 0. This is how we need to calculate. Minus 1.34 into 10 raised to 4 into u3. Next, plus 1.008 into u4 into 10 raised to 4 into u4, which is equal to minus 12 into 10 raised to 3. If you calculate, like if you multiply row and column, you will get these two equations. Once you solve these two equations, you will get the displacements u3 and u4. Minus 0.568 minus 1.9455. These are the displacement at the node 3 in x direction, and this is in x direction, this is in y direction. Once you determine the displacement, the next step is to determine the stresses. Stresses can be determined by using this formula. As we know that this we already discussed in our previous video, the steps to solve the truss numericals and truss problems. So there we have seen the stress formula, E divided by L minus M L M U1 U2 U3 U4, means we are calculating stress in the first element. Here, as we know that Young's modulus is 17 to 10 raised to 3, length of first element is 500, and these direction quotients which we have tabulated for the first element, L is nothing but 1, so here minus 1 is nothing but minus is given, so minus 1, M is 0, 0, L is 1, M is 0, and these U1, U2, U3, U4. So as we know that first node and second node is first node is fixed, so U1, U2 is fixed, and second node we have displacement U3 and U4, which we have found out. If you multiply row and column, then you got this answer. So approximately you will get 79.52 minus 79.52, so approximately 18 Newton per mm square, which we will get the stress in the first element. Again, to determine the stress in the second element, we have this formula, E divided by L2 minus L minus M L M U3 U4 U5 U6, because the second element is connected between node 2 and 3. Second element is connected between node 2 and 3, so node 2 has displacement U3 and U4, and node 3 has displacement, we have U4 and U5. Node 2 U3 U4, here U5 U6 we have. The second element connected between node 2 and 3, and node 2 has displacement U3 U4, and node 3 has displacement U5 U6. So U3 U4 U5 U6, which we have written here, U3 U4 U5 U6. Once you multiply row and column, and if you simplify this, you will get this answer. Yes, you will get the answer which I want you people to determine and comment it below. Once you do that, the reaction forces which we can calculate it by using the formula R is equal to K into U minus F. K is nothing but a global displacement vector, global stiffness matrix. U is nothing but displacement vector, F is load vector. By using this formula, you can determine the reaction at the support. So I want you people to calculate the reaction forces and what is the stress in the second element. You comment below in this video so that I can see how many of you people are really interested in these type of problems. Thank you for watching. If you have any doubts, you can comment below. Thank you.